So what we will look at today
is
adsorption. The parse lectures from last year are all posted. Those include predominantly the theory, some information about isotherms, and for those of you that will be taking the environmental FE, it is on the environmental FE. So I've taken much of that material from the handbook of the FE reference handbook. So what I'd like to do today is just kind of briefly go over what is adsorption and compare it to absorption. So when we talk about adsorption, we're looking at a surface phenomena. So for instance, you can think about this as you have friends over for your in your apartment. You're not a smoker, but your friends are come over, they've been smoking. The next morning, a couple days later, you still smell smoke. Why? What's happened?
Something, the fabric, they consume the smoke.
Exactly. So the particles, okay, the chemicals from the smoke are adsorbed onto the fabric particles. So it's a surface phenomena. Absorption is, if we think about it here, this is my raindrop. I have CO2 in the gas phase, and I measure CO2 in the raindrop. What's happened there? There we have absorption, okay? The CO2, the molecules of CO2 are transferred across the air-water interface into the air, into the water droplet. So think of that as a three-dimensional process where your chemical is actually dispersed throughout the solution. We model them very differently. They behave very differently. So we will look at absorption next, but for now, what we're looking at is adsorption. And since it's only the five of us, if you have a question, just unmute yourself, and happy to make this more of a conversation than a lecture. So there's some terminology that we need to make sure that we understand. When we're talking about the particles, case of the smokers, the fabric, okay, the thing that is actually adsorbing the chemicals is your adsorbent. In water treatment and in wastewater treatment, we're often there talking about activated carbon. We may be talking about activated alumina. We may be talking about some synthetic material, maybe ferric oxides. Okay. So that's the adsorbent. The adsorbate is what's being adsorbed. So in this case, copper ions are what is being adsorbed onto a solid surface, the adsorbent. Okay. We have to talk about an adsorption density. And that is, in this case, it would be the milligrams of copper per gram of solid. And this is per gram of adsorbent. Okay. Or in some cases, because it's a surface phenomena, we'll use milligrams, in this case it would be copper, per meters squared surface area of the adsorbent. Okay, so those are important terms to remember because we'll use them throughout the discussion with adsorption. Okay, so what we'll look at today is we're going to look at a number of problems. The first one we'll look at is powdered activated carbon. So powdered activated carbon is just activated carbon that is very, very fine. It's too fine to use in a column because the head loss would be too great. But kind of think of it, it's the consistency of the powder that you would use on you. Okay, if you it's that fine. Well, we can add this to a rapid mix tank when we add coagulants. So in this case, okay, when we talked about rapid mix and we're adding the coagulant, we're looking at achieving what? So add the coagulant in the rapid mix basin. What are we trying to do with by adding the coagulant?
Remove charged particles.
Okay, we're looking at changing the surface charge and removing those charged particles. Exactly. When we're adding PAC, we may be removing charged particles, but we also may be removing neutral particles. So we're looking at removing material that is what we refer to as typical hydrophobic. Phobic meaning fear, hydro water. So we're often looking at removing those particles that don't want to be in water, that they would rather be on the surface of this carbon than they would rather be in water. And we can add it into the basin. Okay, we can either add it, as shown here, an upper figure, adding it in a sedimentation basin. Okay, we can add it in the rapid mix basin. But what we're doing is we're looking at removing these particles or this material, maybe colloidal. So for instance, in Flint, they used activated carbon to remove the NOM, the naturally occurring organic matter. Why? Because what was happening was their concentrations of disinfection byproducts were too high. So that was resulting from the reaction of the disinfectant with the NOM. So then they started using activated carbon to remove the NOM to try and reduce the concentrations of disinfection byproducts. We'll look at this first example here, where we're looking at adsorption of benzene, and it's onto activated carbon. A equilibrium study has been done, and the data has been modeled using a Freundlich isotherm. And this is the basic equation for the Freundlich isotherm. The screenshot is actually from the FA reference handbook. So this is the equation. X is the mass of adsorbate, and M is the mass of adsorbent. So it's the milligrams of benzene per gram of activated carbon. Those are the units of X over M. And you're told that to start, we have this 1 liter solution to 25 degrees C, okay, and adsorption is an exothermic process. So the data for which that Freundlich isotherm was obtained need or developed needs to be at that same temperature. So it would be at 25 degrees C. And you're told that you have 0.5 milligrams per liter of benzene. That's our starting situation. It's a batch process. So we add the activated carbon to it. We're going to add our activated carbon. We're going to mix. Okay. We're going to allow the adsorption to occur. And then what we want now, we still have 1 liter of solution, but now we have a concentration of benzene of 0.01 milligrams per liter. So this is our equilibrium concentration. So we can write a mass balance for this. So this is our mass of benzene initially. At equilibrium, that mass of benzene is equal to what? Where can the benzene be? So we start with a beaker, okay, 1 liter beaker with 0.5 milligrams per liter of benzene in it. We add activated carbon, we mix it, we allow it to reach equilibrium. We're going to assume we have no reaction of benzene other than the adsorption. So where can my benzene be?
It can be attached to the activated carbon.
Okay, so we have some mass on the activated carbon. And where else can it be?
It can be in solution.
So initially, the mass of benzene, we have 0.5 milligrams per liter. We have 1 liter of solution. So we have 0.5 milligrams of benzene. And that is equal to the mass on the activated carbon. And that is 50.1 times the equilibrium concentration, 1 over 1.88, times the mass of activated carbon plus the mass in solution, which is C sub E, times the volume of water. Okay. So that's 0.5 milligrams is equal to 50.1 times 0.01 to the 1 over 1.88 times the mass of activated carbon, which we don't know, that's what we're looking for, plus 0.01 milligrams per liter times the 1 liter. And we can solve for the mass of the activated carbon, and that is equal to 0.1135 grams. And remember, you keep track of units. Okay, it's milligrams of benzene in this case per gram of activated carbon. And when you're looking at an isotherm or you're given an isotherm, they need to give you the units. Okay, so this is the amount, or we need 114 milligrams of activated carbon. So that's how much activated carbon we need. Questions? So we're using the same theory that we developed very early on with mass balances, and we will use that throughout this unit on activated carbon. Now, if the same adsorbent dose is in this case used to treat a 1 liter solution of 0.5 milligrams per liter toluene instead of benzene, you're asked to determine the equilibrium concentration. So our approach is the same. Okay. The only difference, again, we're looking at a batch system and we're looking at equilibrium. So we start with 0.5 milligrams per liter. Now we're asking, what is that equilibrium concentration? Because in this case, we're going to use 0.1135 grams of activated carbon. So now we have 0.5 milligrams per liter times 1 liter, same as before. We have the mass, in this case toluene, in the water. So that is equal to C sub B times 1 liter plus 76.6 times C sub E, in this case 1 over 2.74 times the 0.1135 grams. And we need to solve for C sub E. Easiest way to do that is in Excel. Set up solver, and in roughly a couple seconds, you get the answer. And the answer is about 4 times 10 to the minus 4 milligrams per liter of toluene. So for benzene, the equilibrium concentration was 0.01. If we have these two chemicals in solution together, so we have a solution with both, and we add the same amount of activated carbon. So we add 114 milligrams of activated carbon. Will we end up with the concentrations that we calculated, or when would we end up with the concentrations that we just calculated? Or what potentially can occur when we have both of these chemicals in solution and we add activated carbon?
Will they absorb at different rates?
When they can absorb at different rates, exactly. So it may take different lengths of time to reach equilibrium. Okay. What else? Can one chemical affect the adsorption of another? Think about Tuesday's lecture by Mike Ellis for PFAS removal. Why did they have essentially a roughing column? The waste that they were treating had a high concentration of organic matter that was not PFAS. But the problem is there may be competition for sites. So in the case of what Mike was talking about on Tuesday, they had this roughing column first to remove the naturally occurring organic matter, the other chemicals that were present in higher concentrations. And then they were using the probably much more expensive activated carbon that was selective for PFAS chemicals for the treatment process. So if there is competition, then one of the chemicals may be preferentially sorbed over another, in which case the isotherm equation that you developed no longer predicts the adsorption. So for this situation we showed, the only if there was no competition and you had benzene and toluene in solution would both of those adsorption isotherms that were developed independently be valid. So that's an important thing to remember. We'll look at a little more complicated situation here, where now we have the adsorption of benzene onto activated carbon. Same isotherm. Now we have a waste solution that contains same concentration of benzene. It's entering a rapid mix tank at a flow rate of 100 liters per second. We have a slurry of powdered activated carbon that we're adding to the rapid mix tank at a flow rate of 1 liter per second. What's the difference between this scenario and the previous one?
We're given a flow rate rather than a solid volume.
Yeah, so we've got a flow rate, so it's a continuous system, right? Before we had a batch system, now we have a flow, we have a system that is flowing. We'll assume that no adsorption occurs in the rapid mix tank because time is insufficient. Okay. The only thing we have that is, or what is happening in the rapid mix tank. So I have a rapid mix tank, I have flow in. This is my waste flow. And that is 100 liters per second. And I have a concentration of benzene equal to 0.5 milligrams per liter. And I have my slurry, and that is equal to 1 liter per second. And I have a concentration of PAC of 2.02 grams per liter. What's happening in my rapid mix basin? What am I trying to achieve?
Since no absorption occurs, is it just mixing?
Exactly. All it is mixing. Okay. So I end up with a concentration out, or sorry, a flow out of 101 liters per second. And I can determine now my concentration of benzene leaving and my concentration of PAC leaving, which we'll do. That flow then, that waste stream, that stream then flows into a flocculation basin. I have sufficient time in the flocculation basin for adsorption to occur. So the adsorption is occurring in the flocculation basin. So I essentially have two mass balances. So we'll start with the first mass balance. So this is our rapid mix tank. We have 0.5 milligrams per liter is my concentration of benzene in the slurry. And we have a flow rate of 100 liters per second. Now the concentration of PAC in my waste is equal to what?
2.02.
Not yet. Concentration of PAC in the waste stream.
Oh, 0.
0. Now we have a slurry. Okay. And the flow rate in my slurry is given as 1 liter per second. The concentration of PAC in my slurry is equal to, here's my
2.02. Yeah.
Yep. And my concentration of benzene in the slurry is 0. So I have a mass balance here, and I can develop a mass balance for both my PAC and my benzene. So we'll develop it first for the PAC. So we have flow rate of the waste stream times the concentration of PAC in my waste stream plus flow rate of my slurry times the concentration of PAC in my slurry, and that is equal to Q out times the concentration of PAC out. Okay, and this we said was 0. So we have 1 liter per second times 2.02 grams per liter that equals 101 liters per second times C running out of space, C out. And CPAC out is equal to 0.02 grams per liter or 20 milligrams per liter. So simple mass balance, no reaction, no adsorption. We can develop same set of equations for Q waste. Now we have C benzene in the waste plus Q slurry times C benzene in the slurry, and that equals Q out times C benzene out. If we substitute in their C benzene out is equal to 0.495 milligrams per liter. We have a slight dilution because of that 1 liter per second. Okay, I didn't write this out, but we've done the mass balance on the rapid mix. So the next thing we want to do is a mass balance on the flocculation basin. So for the flocculation basin, so now here's our flocculation basin, and we've got mixing. Assumed we've got tapered flocculation. So now we have Q into the flocculation basin. That's equal to Q out from our rapid mix. So that's 101 liters per second. C in of PAC is the 20 milligrams per liter or 0.02 grams per liter. And C in of benzene is equal to the 0.495 milligrams per liter that we just calculated. What we're looking for, we'll assume that equilibrium is reached. So we're looking for that equilibrium concentration. So we can write a mass balance for benzene, and that is equal to Q in, C benzene in. And where can my benzene be? At equilibrium, what phases, basically, I'm asking, can my benzene be in?
It can be suspended or attached to the activated carbon.
Exactly. It can be in the solution or on the carbon. It's only we're assuming no reaction. Okay, so it's not decaying, it's not attaching to walls. We're going to assume that the only two places it can be is on the carbon or in solution. So we have C benzene in the water out. Okay, that's our equilibrium concentration times Q, the water out, plus X over M for the benzene, so that equation, times C of the PAC times Q water out. And then this is equal to 0.495 milligrams per liter times the concentration as, times the flow rate, 101 liters per second. We don't know C sub B, so I'm just going to write that as C sub B times 101 liters per second plus same isotherm that we had before, C sub E 1 over 1.88 times, make sure your units are consistent. This was an milligrams per gram. So we want to multiply this by 0.02 grams per liter. So we've added, okay, times 101 liters per second. We need to solve for C sub B. You can also use solver again. And when you do, your concentration, C sub B, which is concentration of benzene, is equal to 0.143 milligrams per liter. Or we can calculate a removal efficiency, and that we started with 0.5 minus 0.143 over 0.5, and that is 71.3%. So that's our removal efficiency. Now, compare that to what we got in the batch system. In a batch system, see, essentially the same, okay? 1 liter, we add PAC, okay? We ended up with 0.01 milligrams per liter. Now the volumes changed, but notice, okay, the isotherm was the same. Your batch system was more efficient than your continuous system. What we've assumed here is a completely mixed system. Given what we did at the very beginning of the semester with reactor theory, is that anticipated? Would you have expected the batch system to be more efficient than a continuous system, a completely mixed system? Because what we've assumed is a completely mixed system. And the answer is yes. If you go back and look at the notes back in reactor theory, okay, when we looked at scenarios, in those cases, we had similar sizes of reactors, and we looked at a batch system versus a completely mixed system. The batch system was more efficient. How could we make our continuous system more efficient? How might we change this?
Can you increase the time that it absorbs for?
Okay, well, we could change the time. We've assumed here that we've reached equilibrium, okay? If we used a plug flow system, so we had a series of reactors, okay, and we used a plug flow system, would we increase the removal efficiency? The answer is yes, okay? I want you to think about that. If you need to go back to the reactor theory notes at the very beginning, if we had a plug flow system, we would improve our efficiency. So we just continually, in that plug flow system, okay, you have a reactor, you allow some reaction, and then kind of that water moves down the system, and we would improve efficiency. So plug flow system will always give you a more efficient removal than a continuous mixed system. We essentially do that with a carbon column. So what we'll look at next is using a carbon column. So essentially what we're doing there is we have this column, we have flow down. We have some portion, we'll go through this, but we have some portion where we have equilibrium. So if we monitor the concentration right here is at equilibrium. Okay. Concentration at that point here is probably 0. But what happens in these systems is that adsorption front moves down the column over time. So now this is C sub B. Now this is C sub B. Okay. And after time, this becomes C naught. I've exhausted, I've used up all the capacity on that resin. And over the next time, okay, so that adsorption zone moves down. This here becomes C naught. So I'm not getting any more removal, and this becomes C, the equilibrium concentration. And eventually, if you let it continue, eventually this becomes C sub B. So eventually, if I monitor volume through the column versus concentration, it's essentially zero. It begins to increase, and eventually it'll reach C naught, because eventually I've used up all the column. So what I've done here is essentially gone from this completely mixed system to a plug flow system. So I can kind of think of each one of these adsorption zones as being a CSTR, but having a sequence of CSTRs down the column. Okay. So that's in next week's processing. I'll look at columns and how they operate. But today we focused on batch and CSTRs. I can do the water tower again.
Yeah, that sounds interesting.
Okay. Well, I will post that, but it's definitely not due next Wednesday.
Okay. Okay, I was worried.
Okay. No, no need to worry.
Okay, thank you.
Okay. You have a great day and a
You
great
too.
weekend.